In 2019, a massive computing cluster churned out 200 gigabytes of data just to solve a problem about stacking bathroom tiles.
Yeah, but these definitely weren't your standard ceramic squares from Home Depot.
No, they were seven-dimensional hypercubes. And the crazy part is the exact same math used to stack those cubes without their faces touching it's the same topological framework currently keeping next-generation aerospace metamaterials from just shattering in midair.
Right. Welcome to the deep dive. Today we're getting into the architecture of the hypercube. No preambles, we're just jumping straight in because, you live in a 3D physical space, but the data you process, the neural networks you train, and the advanced alloys in your hardware, they all operate in no-dimensional space.
Exactly. And to navigate that space, we really need a map. I think a lot of people hear the word hypercube and immediately write it off as like abstract sci-fi geometry.
Oh, totally. Like it's just a CGI effect in a movie.
Yeah, but it is a perfectly rigorous, mathematically bounded structure. The logic scales flawlessly from a single dot on a piece of paper all the way up to infinite dimensions. So if you can visualize how a basic square operates, you already have the foundational logic to understand a non-dimensional universe.
You really do. So let's actually establish that foundation right now.
Hmm.
We start with what's called the Minkowski sum.
Right.
If you take a zero-dimensional point, and you just drag it one unit along an x-axis, you sweep out a 1D line.
Makes sense.
Then you take that entire line and you drag it one unit along a perpendicular y-axis and you sweep out a flat 2D square. Drag that whole square along the z-axis, you get a solid 3D cube.
So the Minkowski sum is basically just formalizing this recursive sweeping motion.
Exactly. A dimensional hypercube is literally just the Minkowski sum of mutually perpendicular unit-length line segments.
Which gives us this highly predictable recursive formula. So if we define a non-dimensional hypercube as Q and Allers, the structure is just two copies of the previous shape, so two copies of Q and Allers, with edges joining their corresponding nodes.
Right, which is literally how everyone draws a 3D cube on a flat piece of paper when they're bored in class.
Yeah, you draw a square, you draw another square slightly behind it, and you just connect the four corners.
Exactly. But when we try to scale that up to 4 dimensions to build a tesseract, we have to take two solid 3D cubes and connect their 8 corresponding vertices.
And the massive structural problem for us there is that those connecting lines, they have to run along a completely new fourth coordinate axis. We have X, Y, and Z. Now we suddenly need a W axis that is simultaneously perpendicular to all three of those.
And that is exactly where human intuition just completely redlines. Our visual cortex is strictly optimized for X, Y, and Z. We literally cannot natively point to a W axis.
I mean, I've tried, and it just gives me a headache.
Right. So we have to rely on lower dimensional representations. We essentially have to look at the shadows. Think about it. When you look at a 3D cube in the physical world, your retina isn't actually capturing 3D geometry. It's capturing a 2D projection.
It's just a flat image parsed by your brain. If you take a wireframe 3D cube and shine a flashlight on it, the shadow it casts on the wall behind it is a 2D projection.
Yeah, and it looks like a smaller square suspended inside a larger square with their corners connected by diagonal lines.
And that logic scales up perfectly. If you take a 4D wireframe tesseract and project its shadow down into our 3D space, it looks like a smaller, solid 3D cube floating inside a larger, solid 3D cube with all their corresponding corners wired together.
But projection is really only one way to map the geometry. The other method is slicing. And this is where the geometry gets actively hostile to our common sense.
Okay, hear me out on this, because slicing makes sense if we just step down a dimension first. Think of an MRI machine taking 2D slices of a 3D human body.
Good analogy.
If you took a solid 3D cube and you pass it cleanly through a flat 2D plane, like slowly dipping a block of ice into a perfectly still pool of water, the intersection, that 2D slice right at the surface of the water, is a solid four-sided square. So scaling that up, if a solid 4D hypercube passes through our 3D physical universe, the 3D slice that we observe is just an entire solid 3D cube appearing out of nowhere.
It is. But I want to pressure test that because the interactive 4D visualization handbooks we're pulling from highlight a specific orientation called the ZW plane rotation, or the color cubes alignment.
Oh man, yeah, this part.
And it completely breaks that clean, intuitive slicing model.
Yeah, this is where visualizing it starts to actually hurt, because the text says if you take a tesseract, which is composed entirely of 8 distinct 3D cubicle cells, and you rotate it strictly on the ZW plane by exactly 45 degrees, the resulting 3D slice isn't a perfect cube anymore.
No, it's not.
You end up seeing 2 square faces and 4 rectangular faces. which makes no sense initially. Where are the rectangles coming from? A tesseract is made of perfect cubes. There are 0 rectangles in its fundamental architecture.
The rectangles are an artifact of the intersection plane. They're foreshortened shadows. Let's drop back to the 3D to 2D analogy for a second.
Right.
If you take a normal 3D cube, hold it flat, and push it straight down through the 2D plane of water, the cross-section is a perfect square. But what if you rotate that 3D cube 45 degrees so it's balancing perfectly on one of its long edges, and then push it through the water?
Ah, right. The slice intersecting the surface isn't a square anymore.
Exactly. It's a rectangle that starts out super narrow, widens out as the thickest part of the tilted cube passes through, and then narrows down again. The angles of intersection are skewed relative to the faces.
So the projection stretches the geometry.
Yeah, precisely. So in 4 dimensions, when we observe a 3D slice that has 2 square faces and 4 rectangular faces, the math is telling us exactly how that tesseract is oriented in the unseen W-axis.
It implies that 2 of the tesseract's constituent 3D cubes are moving through our 3D universe face first, basically hitting the intersection cleanly at 90 degrees, which maintains their square cross-sections.
And meanwhile, the other 4 constituent cubes are hitting our 3D space edge first at a 45-degree tilt. So their internal 3D volume is being literally skewed right across the intersection, distorting their geometry into those rectangles.
I mean, that is incredibly elegant when you think about it. You're effectively tracking the rotation of a 4-dimensional object purely by observing how its 3-dimensional cross-section warps and stretches in real time.
It's like watching a footprint change shape in the mud and reverse engineering the exact angle and velocity of the invisible leg stepping down on it.
That's exactly it, and that is the core of hypercube analysis. We can't see the whole structure, so we have to rigorously count and categorize the pieces we can interact with. Which brings us to the combinatorics.
Right, the numbers game.
How do we precisely quantify the anatomy of infinity? Like if I hand you a 10-dimensional hypercube, how do you mathematically know what's inside it?
Well, we start with the absolute lowest level primitive, the vertices, the corners. The formula for that is beautifully simple. A 9-dimensional hypercube has exactly 2 $2 vertices.
So a 0D point has 2 $, which is just 1 vertex. A 1D line has 201 so 2 vertices. A 2D square has $202, giving 4. A 3D cube is $203, which is 8.
And our 4D tesseract has $284, resulting in 16 individual corners.
The doubling is just a direct physical result of the Minkowski sum, right? Every time you step up a dimension, you duplicate the entire existing structure and shift it.
Yeah, but counting the higher dimensional subcomponents like the edges, the flat squares, the solid 3D cells, it requires a master formula.
Right, big one.
The number of k-dimensional subcubes inside a no-dimensional hypercube is defined as QKN times CKNA.
Let's break down that CKNA part because it is definitely doing the heavy lifting here. That's the standard combination formula, N choose K.
Exactly.
It calculates the number of ways you can pick a subset of distinct items from a larger pool of dollar items, completely ignoring the order you pick them in.
Yeah.
But as an engineer, I look at this and go, why is a statistical combination formula dictating hard physical geometry?
Because at a structural level, geometry is just a physical manifestation of combinatorics. Let's ground this. Pick a single vertex on a non-dimensional hypercube. Because you're in non-dimensions, there are exactly non-dollar independent edges radiating outward from that specific corner.
Right. In a 3D cube, 3 lines meet at every corner. In a 10D hypercube, 10 lines meet at every single corner.
Yeah, the degree of every vertex is no dollars. Now suppose you're standing at that vertex and you want to build a 10-dimensional shape originating from that exact spot. Let's say you want to build a flat 2D square, so $10 too.
Okay.
To define a square, you need 2 orthogonal directions. So you have to choose exactly 2 distinct edges out from the nullars available at your corner. The total number of ways to mathematically select 2 specific edges out of another options is literally the definition of the combination formula code.
It clicks perfectly. So at any given corner in the entire hypercube, there are exactly 10k distinct dimensional shapes attached to it.
Yes. Now, to find the total number of these shapes in the entire hypercube, you might logically assume you just take the total number of vertices, which we established is 2 $, and multiply it by the number of shapes at each vertex.
But wait, if I do that, the math totally falls apart because of overcounting. A square doesn't just have 1 corner, it has 4.
Right.
If I count all the squares anchored to corner A, and then I walk down the edge to corner B and count all the squares anchored there, I'm going to count that exact same shared square multiple times.
Precisely. You've counted every single k-dimensional shape redundantly. Specifically, you've counted each shape once for every single vertex it possesses. And we already know the rule for vertices. Any tau-dimensional shape has $2 vertices.
So to fix the bug in the math.
To correct the systemic overcounting, you take your initial inflated total $2 times CK, K, Medi, via N dollars, and you divide the whole thing by 2 talis N. Using basic exponent rules, $2 divided by $2 leaves you with $2 scalar.
And there is the exact proof for the master formula. $2 times CK, that is incredibly satisfying to unpack. You aren't just memorizing an equation, you're tracing the physical constraints of the geometry.
Let's actually run the tesseract through it to see it work. So 1 other is $4. For edges, $1. We have 16 vertices times 4 choose 1 divided by 2. That evaluates to 32 edges.
For flat square faces, 200 to 2. The formula gives us 24 squares. For solid cubical cells, $203. The formula outputs exactly 8 cubes. So a 4D tesseract is an assembly of 16 points, 32 lines, 24 squares, and 8 cubes.
Then this brings us to one of the most elegant algebraic artifacts in the entire hypercube framework, the powers of 3 rule.
Oh, I love this one.
If you sum up every single structural element of any on-dimensional hypercube, adding its vertices, its edges, its faces, its cells, all the way up to the shape itself, the total sum is always exactly $3.
Let's verify that real quick. For a 1D line, 2 points plus 1 line equals 3 elements. So 3 to 1, $1 for a 2D square. 4 points, 4 lines, 1 square face. That's 9 elements. 302, $2.
For a standard 3D cube, 8 points, 12 edges, 6 squares, 1 solid cube. That adds up to exactly 27 elements. $303.
And for the 4D tesseract we just calculated, 16 points, 32 lines, 24 squares, 8 cubes, and 1 tesseract. That is 81 total structural elements, which is $34.
There is a fantastic historical analog for this that the sources mention. Friedrich Froebel, the German educator who literally invented the concept of the kindergarten in the 1830s, created a series of educational wooden toys called Froebel gifts.
Yeah, the wooden blocks.
Right. Gift number 3 is a solid wooden 3D cube that is physically subdivided by cuts into 27 identical smaller cubes. It's a physical, tactile manifestation of 3D 3-taller Lars.
Okay, I actually have to stop and push back on the topology here, because adding points, lines, squares, and cubes together to get $3 feels like a massive category error. Points have 0 dimensions and 0 volume. Lines have length but 0 area. Squares have area but 0 volume. You're mathematically summing length, area, and volume into a single integer. How is that not just adding apples to oranges to bananas? Without defining a metric space, adding dimensions together is geometrically invalid.
It totally looks invalid if you view them strictly as disparate dimensional measurements. But the proof for the $3 rule resolves this by mapping the combinatorics to a uniform spatial grid.
Okay, map it out for me.
Let's go back to Froebel's wooden toy. Take a standard solid 3D cube. Now, physically slice each of its 3 axes into thirds, like dividing a Rubik's Cube, but solid all the way through. You've just carved the entire volume into 27 identical uniform mini-cubes.
Like a 3 by 3 by 3 grid.
Now map those 27 identical uniform volumes back to the topological features of the original undivided large cube.
Okay.
The dead center of the large cube corresponds to exactly 1 mini-cube in the very middle. The 6 flat outer faces of the large cube correspond perfectly to the 6 mini-cubes situated in the center of each face.
I see where this is going.
The 12 sharp edges of the large cube correspond exactly to the 12 mini-cubes running along the center of each edge. And the 8 sharp vertices of the large cube correspond exclusively to the 8 mini-cubes tucked right into the outermost corners.
Oh, wow. 1 center, 6 faces, 12 edges, 8 corners. That perfectly accounts for all 27 mini-cubes.
Exactly. You aren't adding apples and oranges. You are mapping topological features of varying dimensional rank directly onto a uniform grid of identical volume units. Every single element of the hypercube, regardless of its specific dimension, claims one exact corresponding subvolume in a trisected version of itself.
That is brilliant. And that exact mapping holds true for non-dimensions. If you trisect a non-dimensional hypercube along all its axes, you carve it into 3 non-identical hyperblocks, and every vertex, edge, and face perfectly claims one.
It completely bridges the gap between the abstract algebra and the spatial geometry.
It really does. But as we scale this up, natural language breaks down fast. You can't just keep writing a 5-dimensional shape with 40 flat faces and 10 solid cubes in a research paper. It's incredibly inefficient. Mathematicians needed a universal encoding protocol. Which brings us to Ludwig Schläfli's notation.
Yeah, Ludwig Schläfli was a 19th century Swiss mathematician who practically formalized higher dimensional Euclidean geometry, though his work was tragically basically ignored during his lifetime.
Typical.
Right. But he developed a recursive bracketed shorthand, written as ThiliPUG, that completely defines any regular polytope or tessellation.
The logic of the Schläfli symbol is essentially a functional folding algorithm. The most basic primitive is just Dirichlet, which defines a flat regular 2D polygon with K sides. So is an equilateral triangle, is a perfect square, is a regular pentagon.
And when you step up to 3D, you add a second parameter dash key. The play dictates the foundational 2D shape of the faces, and the telly dictates exactly how many of those faces mathematically fold together to meet at a single vertex.
So a standard 3D cube is encoded as $3. The faces are squares, that's the 4, and exactly 3 of those squares intersect at every single corner, that's the 3.
Right. And scaling to 4 dimensions just adds a third parameter, few q. For our tesseract, the Schläfli symbol is $333.
If you read it left to right, you actually see the entire architectural blueprint unfold. That means you start with squares. The $3 means you fold 3 squares around a vertex to build 3D cubes. And the final $3 means you fold 3 of those solid 3D cubes around every single edge to enclose the 4D tesseract.
The concept of folding solid cubes around a 1D edge is honestly really tough to visualize, but the encoding is mathematically flawless.
And what I find fascinating from a pure engineering standpoint is that this notation exposes hidden structural symmetries through palindromes. It's called dualism.
Oh yeah, duals are wild.
If you take the Schläfli symbol for any geometric shape and completely reverse the numbers, you generate the mathematical dual of that shape. If a shape is a palindrome, like a 2D square, which is just self-dual, but the tesseract is 3-3, reversing that string gives you 3-4.
And 3-4 is not a hypercube. It's an entirely distinct, regular 4D shape known as the 16 cell.
Right.
If you read that symbol left to right, it's constructed from equilateral triangles, the thaler, which are folded 3 around a vertex to form solid tetrahedrons, the 3-taler, which are then folded 4 around every edge to enclose the 16 cell.
So it's basically a hypertetrahedron.
Essentially, yeah. But the dual relationship means these shapes are geometrically linked. The vertices of the tesseract map perfectly, 1-to-1, with the 3D cubical cells of the 16 cell, and vice versa.
The Schläfli symbol isn't just a naming convention, it's practically a computational hash that reveals the inverted symmetrical architecture of the universe.
And that word computational is the perfect pivot, because the hypercube isn't just a theoretical toy for geometry purists.
Not at all.
If you strip away the physical faces and volumes, and you just look at the raw skeleton, the vertices, and the edges connecting them, you're left with a graph, a network structure. And in the 1980s, computer scientists realized that the hypercube graph is arguably the most efficient parallel data routing architecture permitted by physics.
This heavily relies on the concept of Hamming distance. If you take a 9-dimensional hypercube graph, you can uniquely identify every single vertex with a binary coordinate string that is exactly 9 digits long.
Right, so for a basic 3D cube, the coordinates are 3 bits, 0, 0, 0, 0, 0, 0, 1, 0, 10, all the way up to 111.
And the fundamental physical constraint of a hypercube network is that a physical wire and edge only connects 2 nodes if their binary coordinates differ by exactly 1 single bit.
Exactly. Node 0, 0 is wired directly to 0, 0, 1. But node 0, 0 is never wired directly to 0, 11 because those addresses differ by 2 bits.
And the absolute number of mismatched bits between any 2 nodes in the entire network is their Hamming distance. And that Hamming distance translates directly to the minimum number of network hops required to pass a packet of data between them.
Which brings us to the actual hardware. The sources detail the legend of the connection machine. In the 1980s, researchers at MIT and Thinking Machines Corporation were trying to build massively parallel supercomputers. They built the CM1, which utilized 65,536 individual physical processors.
Which was a massive deal at the time. And to make 65,000 processors talk to each other efficiently without creating a catastrophic data bottleneck, they wired them together using a 16-dimensional hypercube network architecture. Because 216 is exactly 65,536.
Right, and here's where it gets insane. Because they use a 16D hypercube topology, the maximum Hamming distance between any 2 of those 65,000 processors is just 16 bits.
That means any node can blast a data packet to any other node in the entire supercomputer in a maximum of just 16 physical router hops. It is insanely efficient.
But, and there's always a but, physicalizing an abstract 16-dimensional mathematical graph using real silicon chips and copper wires introduces massive engineering nightmares.
Oh yeah, crosstalk, routing density, thermal management.
Exactly. And the most famous physicist of the 20th century actually had to step in to solve it.
You're talking about Richard Feynman.
Yeah. Feynman was brought in to consult on the connection machine. The engineers had the hypercube graph, but they were terrified of message collisions. If thousands of processors are passing packets across the hypercube edges simultaneously, what happens when 2 packets need the exact same wire at the exact same millisecond.
A jam.
Right. And Feynman didn't just look at the geometry. He modeled the hypercube network as a thermodynamic system. He wrote out systems of differential equations to calculate the precise buffer sizes needed at every vertex to ensure that message traffic wouldn't overflow the silicon routers during a parallel broadcast.
And this brings up a crucial physical limitation that mathematicians classify under topology, the genus of a graph. When you actually manufacture a motherboard or a VLSI, a very large-scale integration chip, you are printing a network onto a flat 2D silicon wafer.
And a flat plane is a surface with a genus of 0L. It has no topological holes.
But we know that you can't even draw a 3D cube on a flat piece of paper without the inner lines crossing. In a physical circuit board, crossed lines mean short circuits. You literally fry the machine.
Exactly. So mathematicians determine the topological genus of a graph, which essentially asks, what is the absolute simplest surface on which we can embed this entire network without a single edge crossing another?
A surface with one hole, like a donut or a torus, has a genus of 1. Ringle's theorem for orientable surfaces provides the exact formula for the hypercube. The genus is calculated as 1 and 4, 2 and 3 plus 1.
So if we plug in 1 to 44 those for a tesseract, the formula gives us $D times 21 plus 71, which is exactly 1.
Meaning you can draw a 4D tesseract graph perfectly with 0 crossed wires if you draw it on the surface of a donut.
But as dimensions scale, that genus explodes exponentially. If you want to print a 6-dimensional hypercube network, the formula dictates a genus of 17. You need a 17-hole surface just to untangle the wires.
When engineers build hypercube computers, this topological knottedness dictates exactly how many separate insulated layers the printed circuit board requires, or how many vertical silicon vias need to be drilled just to prevent signal interference.
The abstract topology directly dictates the manufacturing constraints of the hardware.
It's unavoidable. So we've established that hypercubes build flawlessly efficient, albeit highly knotted, internal networks. But what happens when you take these rigid geometric shapes and try to stack them outward to fill infinite physical space?
This leads us to one of the most frustrating problems in modern geometry, Keller's conjecture. Introduced by Otto Heinrich Keller in 1930, the premise is deceptively simple.
It states that in any possible tiling of non-dimensional Euclidean space using identical hypercubes, there must be at least 2 hypercubes that perfectly share a complete, fully flush, die and one-dimensional face. Let's contextualize this so it's not just abstract math. Imagine you're tiling a bathroom floor with identical 2D square tiles. You want to cover the entire infinite floor without a single gap and without any tiles overlapping.
Right, a perfect tessellation.
Keller's conjecture says that no matter how weird or erratic your pattern is, at least 2 of those tiles must touch completely edge to edge somewhere on that floor.
Which feels intuitively obvious. Even if I try to slide the rows or offset them like a brick wall, the tiles still share partial edges. And because the plane is rigid, eventually the constraints of geometry force 2 tiles to align perfectly flush. The conjecture holds absolutely true in 2D, and mathematicians quickly proved it true for 3D cubes as well.
But as you add spatial dimensions, you add degrees of freedom. You add spatial wiggle room for the hypercubes to slide past one another.
And the fundamental question was whether the massive volume of higher dimensions offered enough wiggle room to construct an infinite repeating tiling pattern where absolutely no 2 hypercubes ever shared a fully flush face. And the history of cracking this is honestly a masterclass in cross-disciplinary translation. Because you can't just physically stack 7-dimensional boxes in a lab to test it.
No, you definitely can't.
So in the 1940s, a mathematician named Hajos translated this pure geometry problem into abstract algebra. He turned the physical hypercubes into factorizations of abelian groups. He stripped away the spatial dimensions and turned the tiles into grids of discrete numbers.
And then in 1990, Karate and Sabot took Hajos' group theory and translated it again, this time into graph theory. They created what are now explicitly known as Keller graphs.
The rules of a Keller graph are brilliantly specific. Let's break down the translation. In a Keller graph of dimension $, the vertices aren't corners. They're coordinate strings made entirely of the numbers 0, 1, 2, and 3.
Okay.
The graph connects 2 vertices with an edge only if they meet 2 extremely strict conditions. First, their strings must differ in at least 2 coordinate positions. Second, they must differ by exactly 2, modulo 4, in at least one of those positions.
That modulo 4 arithmetic is the key. In this translated model, the number 0, 1, 2, and 3 represent the physical positions of the hypercubes. The rule that the coordinates must differ by exactly 2 acts as an anti-overlapping mechanism.
Right.
In modulo 4, a difference of exactly 2 represents distance of exactly 1/2 of a cube's width. It perfectly spaces the tiles out so they physically butt up against each other without intersecting in space.
Okay, so that handles the overlap. What about the flush faces?
That's the first rule. The coordinates must differ in at least 2 distinct positions. If 2 cubes differ in only 1 dimension, they are sitting perfectly flush against each other. By forcing them to differ in at least 2 dimensions, you ensure the cubes are shifted just enough across multiple axes that they slide past one another.
Ah, so they might share a partial edge or corner, but they will never share a full, completely flush face.
Exactly. So the graph's mathematical constraints are the literal physical constraints of the hypercubes. Karate and Sabo proved that if a computer could find a click in this graph, a specific subgraph where every single vertex is perfectly connected to every other vertex, and that click contained exactly $2 nodes, then Keller's conjecture was totally false.
Because finding a click of that exact size means you've mathematically packed enough hypercubes into a localized volume, completely obeying both the anti-overlap and anti-flush face rules to establish a repeating, interlocking pattern that will tile the entire infinite universe.
So the hunt was on for these cliques, and the progression of discoveries is wild. In 1992, Ligarius and Shor analyzed the Keller graph for 10 dimensions. They found the clique, conjecture proven false in 10D.
Which is huge.
Shortly after, a mathematician named Mackey optimized the search and found a clique in 8 dimensions, false in 8D. But dimension 7 and below remained a total black box because the Keller graph for dimension 7 is computationally astronomical. Searching it for cliques requires evaluating a massive combinatorial explosion of subgraphs.
All right, the graph size grows exponentially, and clique finding is a famously NP-hard problem. We deal with this in AI optimization all the time, but the stalemate finally broke in 2019.
Right, the 200 gigabyte proof.
Yes. A team of computer scientists, including Mackey, utilized massive parallel processing to run a 200 gigabyte computer-assisted proof. They didn't just brute force it, they used advanced SAT solvers and symmetry breaking algorithms to aggressively prune the search space, basically discarding redundant graph permutations before the computer even had to check them.
And after crunching 200 gigabytes of proof data, the SAT solver delivered the final verdict. The absolute maximum clique size for the 7-dimensional Keller graph is 124.
And 27.7 is 128.
Exactly. 124 is less than 128. The clique is incomplete. The pattern physically cannot be closed. Therefore, in 7-dimensional space, the hypercubes must eventually touch face-to-face.
So the 90-year mystery was solved. Keller's conjecture is true, but only for spaces of 7 dimensions or fewer. The moment you step into dimension 8, the universe suddenly has enough topological wiggle room for infinite cubes to slip past one another forever.
It's a stunning example of how spatial intuition utterly collapses at a specific dimensional threshold. So, while Keller was obsessed with stacking infinite hypercubes together, other geometricians were hyper-fixated on taking a single hypercube and slicing it cleanly down the middle.
Which leads us to the concept of central sections.
When we talk about a central section, we mean taking a non-dimensional hypercube and cutting it with a flat n-dimensional hyperplane that passes exactly perfectly through its dead center. The core objective is to calculate the precise n-dimensional geometric volume of that exposed slice.
It seems simple enough in lower dimensions. If you have a 2D square and slice it diagonally through the center, the resulting cross-section is a 1D line segment. If you slice a 3D cube flat through the middle, the section is a flat 2D square.
Right.
The sources dive heavily into the work of Pornin, who extensively studied the main diagonal section. This is the specific slice you get when you cut the hypercube perfectly perpendicular to the main diagonal axis, running from one extreme corner to its exact opposite.
And Pornin mathematically proved that for any hypercube of dimension 4 or higher, the volume of this diagonal slice is strictly locally maximal.
Meaning if you tilt your slicing hyperplane even a fraction of a microscopic degree in any direction, the surface area of the resulting cut instantly gets smaller. The main diagonal represents a peak in the volume topology.
Which is a beautiful, pure geometry proof. But here is the massive pivot. The mathematical machinery used to calculate the physical, spatial volume of these hypercube slices. It's the exact same mathematics used in probability theory to track random events.
Specifically, it maps to the Irwin-Hall distribution.
Yeah.
The Irwin-Hall distribution models the probability density for the sum of independent random variables that are uniformly distributed between segment 1 and 1.
Okay, let's ground that. Imagine you're rolling a set of weird, continuous theoretical dice. These aren't standard 6-sided dice. They can land on literally any microscopic decimal value between -1 and 1.
Like 0.45 or -0.9.
Exactly. If you roll a dollar of those dice and add the results together, the Irwin-Hall distribution tells you the probability of hitting a specific sum. The sources introduce the Laplace-Polya integral, which is the exact equation used to calculate that probability.
And if you take that same Laplace-Polya integral and apply it to a non-dimensional hypercube, it perfectly calculates the geometric volume of a slice intersecting the cube at a distance from the center.
Wait, pause. This is where we need to connect the wiring, because my engineering brain is throwing an error. Why would rolling theoretical continuous dice have anything whatsoever to do with the physical surface area of a sliced five-dimensional box? Where is the causal mechanical link between statistical randomness and solid geometry?
The connection is the coordinate space itself. Think about a standard unit hypercube centered at the origin. Its physical boundaries on every single axis are strictly defined by the interval between -1 and 1. The x-axis extends from -1 to 1. The y-axis extends from -1 to 1.
Okay.
Now map that back to your continuous dice. Every single independent die roll is bounded perfectly between -1 and 1.
Oh, so every single possible outcome of those dice rolls corresponds to a literal physical set of coordinates. If I roll 3 dice and get 0.5, -0.2, and 0.8, that represents an exact pinpoint dot inside a solid 3D cube at x equals 0.5, y amount 0.2, z 0.8.
Precisely. The hypercube is the physical embodiment of the statistical sample space.
Mm-hmm.
It contains every single possible reality of those dice rolls within its volume. Now, when a statistician asks, what is the probability that the sum of these variables equals exactly $2, they are mathematically defining a rigid condition, 6 dactyls plus y plus z equals r other.
But in geometric calculus, the equation 6 dactyls plus y plus z isn't just a condition, it is the literal mathematical definition of a flat hyperplane cutting through 3D space.
Yes. So the physical slice cutting through the hypercube literally contains every single coordinate point where the dice happen to sum up to dollars. Calculating the statistical probability of that sum occurring is mathematically structurally identical to calculating the physical volume of the geometric slice intersecting the hypercube. The probability density is the volume.
That is mind-bending. The math of randomness is just the geometry of hypervolumes, and the text notes this goes even deeper into combinatorics. These specific volumes can be calculated using Eulerian numbers of the first kind.
Right, which are combinatorial integers that count the number of permutations of a sequence where exactly a certain number of elements are strictly greater than the previous element.
So, just by slicing a hypercube with a plane, you are simultaneously calculating continuous probability distributions and discrete combinatorial permutations.
The hypercube acts as a structural skeleton key, linking geometry, statistics, and combinatorics. And what's truly remarkable is that in recent years, engineers haven't just left this in the realm of theory. They have taken this non-dimensional skeleton key and used it to predict catastrophic failures in physical, real-world materials.
This is where we bridge from pure math to applied material science. The sources highlight a pivotal framework by Marcelo Epstein titled Hypercubes, Non-Groupoids, and Mixtures.
Epstein basically addresses how scientists study complex composite mixtures. We're talking about advanced synthetic alloys, metamaterials, or multi-composites used in aerospace and manufacturing.
Right. When you mix $1 different chemical constituents together, predicting how their microscopic crystalline structures will bond is incredibly difficult. Epstein models this complex mixture using the skeleton of an n-dimensional hypercube.
He introduces a concept called a material groupoid. In abstract algebra, a groupoid is essentially a category where every single mapping, or morphism, is reversible. In material science, a non-groupoid is an algebraic structure used to rigorously define whether different microscopic neighborhoods of a mixed material are physically indistinguishable from one another.
It's a highly precise mathematical measure of material uniformity.
And the edges of the hypercube represent these relationships. Epstein's paper refers to these edges as arrows, or more technically, one-jets of local diffeomorphisms.
Let's unpack one-jets of local diffeomorphisms because it sounds impenetrable, but it's actually a very physical concept. A diffeomorphism is just a smooth, continuous mapping that deforms one space into another without tearing it.
Right.
A one-jet is basically a mathematical snapshot, like a Taylor series expansion truncated at the first derivative. It captures exactly how a microscopic neighborhood of constituent A physically stretches, shears, or rotates to align with a microscopic neighborhood of constituent B.
So the vertices of the hypercube represent the individual material constituents, and the edges connecting them are these one-jets, the exact mathematical blueprints of how the crystalline structures physically deform to bond with each other. It turns the hypercube skeleton into a massive, weighted, directed graph.
But we have to clarify a critical distinction here. If I have a block of advanced alloy sitting on a lab bench and it's mixed from 5 different elemental constituents, that physical block exists in standard 3D space.
Obviously, yes.
So why are we mapping a 3D physical object onto a 5-dimensional hypercube graph? It's because, in this specific application, the dimensions of the hypercube do not represent physical spatial axes like x, y, and z.
No, they represent degrees of physical relationship. If you mix 5 elements together, constituent A is not just linearly bonding with constituent B. Constituent A is simultaneously bonding with B, C, D, and E in a shared matrix. Constituent B is simultaneously bonding with all the others.
The combinatorial explosion of those simultaneous physical relationships is way too dense to map on a 3D grid. The 9-dimensional skeleton of the hypercube naturally organizes that exact combinatorial explosion without losing any localized interaction data. It is the ultimate relationship flowchart.
And Epstein's framework uses this flowchart to test for microscopic flaws. If you trace a path along the edges of this hypercube, mathematically composing the structural deformations of the constituents, you can calculate the overall uniformity of the alloy. Epstein states that if the total calculated weight of a closed circuit around any of the hypercube's square faces evaluates to 0 a condition he terms commutative two faces, then the mixture is perfectly structurally uniform. The constituent metals have blended seamlessly without introducing any internal structural tension.
But if the mathematical weight of that circuit does not vanish, the hypercube has just mathematically detected a physical flaw. Epstein calls this a defect of misalignment.
Exactly. This is critical. You could have 5 distinct elements that are completely structurally flawless on their own. But when you map their simultaneous deformations across the hypercube graph, the non-commutative faces reveal that they are geometrically incompatible when forced to share a unified matrix. They create microscopic dislocations and disclinations.
Which is how you get shear failure. If you are manufacturing a turbine blade for a jet engine out of a new 6-element superalloy, you desperately need to know if there is a microscopic defect of misalignment embedded in the crystal lattice. Because under 10,000 RPMs of thermal stress, that microscopic non-commutative defect becomes a macroscopic crack, and the blade shatters.
Epstein's hypercube groupoids allow engineers to mathematically predict the structural failure points of a synthetic metamaterial before a single physical prototype is ever cast in a foundry.
The abstract algebra of infinite dimensions is quite literally keeping airplanes in the sky. It is the ultimate validation that pure mathematics is never truly disconnected from physical reality.
It really is.
Yeah.
We've traced an incredible arc today, so let's lock this down with some concrete takeaways you can actually use to frame these concepts.
I'll start. Number 1. Dimensionality is just recursive logic. A 4D tesseract isn't magic. It's exactly what the Minkowski sum dictates: 2 3D cubes connected at their corresponding nodes, mathematically expanding the $2 times CKN combinatorics.
Number 2. Networks mimic topology. If you are routing complex data, whether that's 65,000 processors in a connection machine or modern distributed cloud architectures, the Hamming distance of a hypercube graph provides the most perfectly optimized routing paths physics will allow, constrained only by the topological genus of your physical hardware.
Number 3. Infinity has structural constraints. Keller's conjecture and its 200-gigabyte computational proof demonstrate that purely theoretical geometries, like 7-dimensional tiling, can be flawlessly mapped to discrete graph theory and solved using SAT algorithms. Space behaves differently when you add enough dimensions.
Number 4. Probability is geometry. The Laplace-Polya integral proves that calculating the statistical probability of random continuous variables is functionally identical to calculating the physical volume of a hyperplane slicing through a non-dimensional hypercube. Randomness has a physical shape.
And number 5. Abstract math builds physical materials. Epstein's material groupoids prove that you can map the microstructural deformations of complex alloys onto the edges of a hypercube to predict physical defects of misalignment.
It is the ultimate architectural blueprint. But I want to leave you with one final unresolved thought. We spent a lot of time on probability. We established that the precise volume of a d-dimensional cube slice represents the probability of completely independent random variables. Independent continuous dice rolls map perfectly to the rigid orthogonal x, y, and z axes of the hypercube.
Right. Because the axes are mutually perpendicular, they have zero influence on each other.
Right. But what happens to the physical geometric shape of the hypercube when those variables are entangled or mutually dependent, as they fundamentally are in the realm of quantum mechanics? If the variables dictate the coordinate space and the variables become quantumly entangled, does the rigid, perfectly orthogonal skeleton of the nine-dimensional hypercube begin to warp, bend, or fracture?
Could a distorted non-Euclidean hypercube serve as the visual geometric map for the weirdness of quantum entanglement itself? Does the hypercube hold the geometric blueprint for quantum reality?
That is a massive question.
It is. Find your weirdest edge case and share it. We live for that. Tell us what to cover next. Drop a comment and rating. Subscribe if you're into it. Thanks for listening. Catch you next time.